Welcome to lecture 22, where we'll learn a little bit more about flip-flops. Today, we're going to talk about the positive edge triggered JK flip-flop, and the input-output table for this device is shown over here on the left, and the symbols that we might use in a diagram are either one of these on the right. And let's try to summarize what's going on here in the table. Much of this should be familiar to you now. Let's go ahead and look first at the final 6 lines of this table. And basically what they say is that as we would expect for a positive edge triggered device, nothing will happen as long as the clock is constant and equal to 0, or constant and equal to 1, or whenever there is a negative edge. In any of those cases, you can do anything you want to with J and K, and it won't make any difference. The next value of Q will still be the present value of Q, and the next value of Q complement will be the present value of Q complement for all 6 of those cases. The only time that anything happens with a positive edge triggered device is when we have a positive edge for the clock signal. And what happens is summarized in these first 4 lines of the table. And what happens is this. If J and K are both equal to 0 when there's a positive edge, then we just keep doing what we're already doing. In other words, the next value of Q will be equal to the present value of Q, and the next value of Q complement will be equal to the present value of Q complement. If J is 0 and K is 1 when we have the positive edge, then that will force the output Q to 0, and of course its complement will be 1. On the other hand, if J is 1 and K is 0 when there's a positive edge, that will force the output to 1 and its complement to 0. And when J and K, if J and K are both equal to 1 when there's a positive edge, then this is like the toggle condition in the T flip-flop. It'll just toggle our output. So the next value of Q will be the present value of Q complement, and the next value of Q complement will be the present value of Q. And that's it. That summarizes how the positive edge triggered JK flip-flop works. And so now let's do as we did with our previous cases, and let's try to do an example problem. And by the way, as I've noted over here on the right, this diagram that I have here for C, J, and K, you'll be using this same diagram for the test problems. Okay? So let's try to figure out if we were talking here about a positive edge triggered JK flip-flop, let's see how we would fill in the rest of this information for Q. Okay, well, since it's a positive edge triggered JK flip-flop, the positive edge triggering tells us we're only interested in the positive edges of the clock signal. And so those will be at time 0, 2, 4, 6, and 8. Those are the only times when the output can change. And so let's see what happens. At this first positive edge at 0, we have J is equal to 1 and K is equal to 0. And if you remember, up here in the table, when J is equal to 1 and K is equal to 0 at a positive edge, this will force the output Q to be 1, and its complement, of course, will be 0. So we will go here at time 0, Q will be forced to 1. Now, we can immediately go ahead and extend that all the way until just before time 2, because that's our next positive edge. And at that next positive edge, at 2, we have J is equal to 0 and K is equal to 0. And recall, if J and K are both 0, as we see up here, that says keep doing what you're doing. The next value of Q is the present value of Q. Next value of Q complement is the present value of Q complement. So we'll go right through that positive edge and just keep doing the same thing. And let's come over here to just before 4, because that's our next positive edge. Okay, at this positive edge, we see that j is equal to 1 and k is equal to 1. And remember that when j and k are both 1, that is the toggle condition. So the next value of q will be the present value of q complement. And therefore, since the present value of q is 1, the next value of q will be 0. Now let's go to the next positive edge, which is over here at 6. So we'll extend our output all the way to just before 6. And then at 6, we see that j is equal to 0 and k is equal to 1. Now when j is 0 and k is 1, that's this condition here, which forces the output to 0. But our output is already 0, so it just stays there at 0. And we can extend the line all the way over until just before the next positive edge, which occurs here at time 8. And at that positive edge, we see that j is equal to 1 and k is equal to 1. We know that j is equal to 1, k is equal to 1 is the toggle condition. And so since the present value of the output is 0, the next after that will be 1. And that finishes the output for this problem. So for this would be the appropriate output signal if this diagram refers to the inputs for a positive edge triggered JK flip-flop. Now, I'll go ahead and erase that because we're going to be using this same diagram for the test problems, and we'll go ahead and talk about those now before talking about anything else. So the test problems, there are 2 in-class test problems, 22.1 and 22.2, and then there will be one to be presented in class, which will be 22.3. And I just want to make sure, I think this is all very straightforward, but I want to make sure you understand it. So let's go over this. 22.1 says if this diagram refers to a negative edge triggered JK flip-flop, now we just did the case, we just used this diagram and figured out what Q would be for a positive edge triggered flip-flop, but now in 22.1 we want to consider a negative edge triggered JK flip-flop. So it says if this diagram refers to a negative edge triggered JK flip-flop, list all the times at which Q will change from 0 to 1. And the choices are 3 and 9 for A, 3, 5, and 9 for B, 1, 3, and 5 for C, or 1, 3, and 9 for D. And now 22.3, I just want to make sure you understand this, is once again, same diagram. It says, if the C, J, and K signals shown in the diagram were for a positive edge-triggered JK flip-flop, and if the initial value of Q were 1 instead of 0, list all the times at which Q would change from 0 to 1. So what is this saying? Well, it's saying use the same top 3 lines. The C, J, and K signals are the same, but now it's saying suppose that the initial value of Q were 1 instead of 0. So what that means is assume that, you know, by initial value we mean at time 0. Here's time 0 right here. This is the initial value. And so let's say that in this problem what we're supposing is that Q is up here at 1 when we come to time 0 instead of being down here. Let me redraw that. So let's suppose that it were equal to 1 up there instead of down here at 0. So that's what's happening in 22.3. Is it's saying we have these same CJ and K signals, and we have a positive edge triggered JK flip-flop, just as we did in our example, the example that we did a few moments ago. So all of that's the same, but now we're going to assume that the initial Q is up here at 1 instead of down at 0, as we did for the example in the lecture. So if that were the case, then you want to list all the times at which Q would change from 0 to 1, and the choices are 8 for A, 0 and 8 for B, 0 and 4 for C, 4 and 8 for D. And then question 22.3 will be given in class. So now, the last thing I want to do in this lecture, that's all for the test. That's the only test for this lecture. But there is one more topic. It'll be very brief, but one more topic I'd like to discuss, and that's the topic of characteristic equations for the D, T, and JK flip-flops. And characteristic equations refer simply to equations that allow us to summarize the behavior of the flip-flop in a very condensed form. And so let me give you an example. For the D flip-flop, we have the next value of Q is equal to D. Now this, when we have this characteristic equation, we need to understand the next value of Q as meaning the next value of Q immediately after a triggering event. So this would be immediately after a positive edge if we're talking about a positive edge triggered D flip-flop, or immediately after a negative edge if we're talking about a negative edge triggered D flip-flop. But as long as you understand that, then you see that this equation summarizes what we said about the D flip-flop, which is that the output is just a delayed version of the input D. So, in other words, the next value of Q, that value of Q you're going to get right after the triggering event, is just the value of D that you have at the time of the triggering event. So that's a very simple summary of how the D flip-flop works. Now, what about the T flip-flop? Well, the characteristic equation for the T flip-flop is the following. We have that the next value of Q is equal to T ANDed with the current value of Q complement, and then that gets ORed with T complement ANDed with the current value of Q. And of course, that is the same thing as T exclusive ORed with Q. Now, the second part of that equation there, where we say that TQ complement or T complement Q is equal to T exclusive OR Q, that's just a definition, so there's not really anything to understand there. But let's see if we can understand this first part of the equation. Why is the next value of Q, why is this expression here a valid expression for the next value of Q when we have a T flip-flop? Well, remember that for a T flip-flop, when we have T is equal to 0, the next value of Q is equal to the present value of Q. And when T is equal to 1, we want to toggle, and the next value of Q will be the present value of Q complement. Now let's see if that's consistent with this equation. So if T is equal to 0, that would knock out this first term. And of course, if T is 0, then T complement would be 1. And so in the case T equals 0, this gives us Q complement is equal to Q. And that's exactly correct. As we said, when T is equal to 0, the next value of Q is going to be the present value of Q. However, when we get the toggle signal, in other words, when T is equal to 1, the next value of Q should be the present value of Q complement. Let's see if that works. Well, when T is equal to 1, this term, T complement, will be 0. 0 ANDed with anything is 0. So this term will drop away when T is equal to 1. And 1 ANDed with anything is that thing itself. So we'll have 1 ANDed with Q complement is Q complement. So sure enough, when T is equal to 1, we get Q complement is equal to next value of Q is equal to the present value of Q complement, which is exactly right for the behavior of the T flip-flop when T is equal to 1. So indeed, this equation does very simply summarize the behavior of the T flip-flop. And so there's your characteristic equation for it. And now for the final characteristic equation, we want to consider the characteristic equation for the JK flip-flop that we've just considered in today's lecture. And that will be the following. We have that the next value of Q will be equal to J Q complement or K complement Q. Now let's see if we can understand this equation and why it makes sense. Well, remember, the first thing we have for the JK flip-flop is we can look up here, we can remind ourselves in the table. When J and K are both 0, the next value of Q is just the present value of Q. So let's see if that works. If J and K were both 0, well, if J were 0, that would knock out this first term. And if K is 0, well, K complement would be 1. 1 ended with Q would be Q. And we'd get Q complement is equal to Q. And that's correct. If J and K are both 0, we just keep doing what we're presently doing. So that looks good. Now, what about the next one? 0, 1. Well, when J is 0 and K is 1, that should force the next value of the output to be 0. Let's check that down here with this characteristic equation. If J is 0 and K is 1, well, if J is 0, that makes this first term 0. And if K is 1, 1 complement will be 0. So this will be 0 as well. And so we have 0 ORed with 0, which is 0. So when J is 0 and K is 1, indeed, we have the next value of Q will be 0, which is consistent with what we have right here. So again, the characteristic equation looks good. Now, what about the next case? And the next case will be 1, 0. J is 1, K is 0. And in that case, Q complement, the next value of Q will be 1. Well, let's see if that works out. If J is 1 and K is 0, well, if J is 1, this first term, 1 ended with Q complement is Q complement. So the first term becomes Q complement. Now, if K is 0, then 0 complement is 1. 1 ended with Q is Q. So in the case when J is 1 and K is 0, this will say the next value of Q is equal to Q complement or Q. But remember, anything ORed with its complement is 1. So Q complement ORed with Q is 1. So we would conclude that when J is 1 and K is 0, the next value of Q is 1. And sure enough, of course, that is consistent with the third line of this input-output table for the JK flip-flop. And now the final condition that we need to check is when J and K are both equal to 1, we hope that then the characteristic equation will give us that the next value of Q is the present value of Q complement. Let's check and see if that's right. If J and K are both 1, well, if K is 1, 1 complement will be 0, and 0 ANDed with anything is 0, so this term will drop out. And if J is 1, one ended with Q complement is Q complement, and so sure enough, we do get that the next value of Q is the present value of Q complement. So those are the characteristic equations for the D, T, and JK flip-flops. So again, these are your test problems, and the problem that you'll have in class will also refer to this diagram. So if you want to perhaps put that in your notes, it will make it easier for you to go ahead and work on that problem when the appropriate time comes. Otherwise, that is it for this lecture, and so good luck.